Hi friends, so today I'm going to start lecture 32 in our helicopter dynamics course, and today I'm going to be discussing periodic differential equations and how to solve them. Remember that such equations occur in the context of blade flapping as well as general rotor dynamics motion. I'm Dr. Ranjan Ganguly. Now we know that here we have a system which is periodic, and the presence of periodic terms takes place in the forcing, primarily in forward flight. And therefore, Fourier series would be a natural fit to rotor problems because whenever you have periodicity, Fourier series is a very good way to solve such problems because periodic functions can be represented very well in terms of Fourier series. So since the forcing is periodic, the steady response must also be periodic. So let's again go to our simple flapping equation for the blade. And this flapping equation is often a good way to demonstrate any problem in rotor dynamics. So here we have a rigid flap with an offset hinge. So we have nu beta square as the natural frequency of the system. And you now turn your gaze to m beta bar, which is the force or the moment coming from the aerodynamic components. So remember, gamma is related to density of air. So therefore, this term essentially is coming because of the presence of air here. If you are in vacuum, this term will not be there. Now, m beta bar contains periodic terms. So we are solving a differential equation which is periodic. So it is natural to assume a Fourier series as the solution of this differential equation. So we assume the solution of the form beta psi is this series here. So there is a constant term. Then there are two terms in what are known as the first harmonics, that is cosine psi and sine psi. So these are called the first harmonics, beta 1c, beta 1s. Then you have two terms which are in terms of cosine 2 psi and sine 2 psi, and these are called the second harmonics for this particular motion. So sometime you will see rotor dynamics people talking about the 2 per f component of the response or the 1 per f component of the response. So essentially 1 per f component, they mean the beta 1 c and beta 1 s term. The 2 per f component, they mean the beta 2 c and beta 2 s term. Beta 0 is the coning or the steady term. And in general, we can write this as a Fourier series, and there are going to be an infinite number of terms, theoretically speaking, to completely capture the response. Okay, so these are essentially known as the harmonic. So in general, when we write it in this form, you have the harmonic number n, small n being the number there. So that's our Fourier series representation of the solution, and we know that these beta terms are the Fourier coefficients, and the period of the response is 2 pi, which is the span around the rotor disk of angle psi. Okay. Now these constants beta 0, beta 1c and beta 1s are constants with respect to time. The time part has been shifted to these sinusoidal components. And therefore these components beta 0, beta nc and beta 1s, beta ns represent the steady component and the harmonic content of the motion. This is the steady component beta 0, and these are the harmonic content of the motion. Sometime beta 1c and beta 1s are known as the first harmonic, and all 2 and beyond in terms of small n are known as the higher harmonic spectrum or components of the response. Now, if we have the value of beta from some solution procedure, we can also filter out various harmonics of the system by performing these integration. So there are situations where you may actually obtain the solution beta using some numerical method, maybe Runge-Kutta or some time integration, but you can extract out the harmonics from that particular response. Now, this approach is a good way to obtain a steady state solution for the problem. We need only the first few harmonics here. So you see that up to the 3 harmonics will give us a good solution for this problem. Now, this of course depends on the kind of forcing you have. If your forcing is very complicated and there is a lot of excitation taking place at a higher harmonic, then you will require more harmonics to solve this problem. So there are basically two primary ways for using a Fourier series solution to solve periodic differential equations here. The first approach is known as the harmonic balance method, and the second approach is known as the operational method. So I am now going to discuss both these methods very briefly. So let us start with the harmonic balance method. Now here you assume a finite series. Note the word finite. So I have truncated this series to this capital N number of terms. Now in general the Fourier series would have infinite number of terms, but I don't have time to keep an infinite number of terms here. So maybe I take the first 5 terms or the first 10 terms of this Fourier series. And then I substitute this into the differential equation, collect all the like harmonics. So which means I move everything to the left hand side. I take all the coefficients which are constant. I take all the coefficients which are sine psi dependent, which are cosine psi dependent, which are sine 2 psi dependent, cos 2 psi dependent, and so on. Okay, I have truncated it here, but you can go into sine 3 psi, cos 3 psi, and so on. Then set each term in this bracket to 0 and solve the resulting equations which you get. Those will give you the values of the beta 0, beta nc, and beta ns. The second method is known as the operational method. Now here you take your differential equation and you solve these particular equations. So essentially you take your differential equation, multiply by d psi, integrate it from 0 to 2 pi. Similarly, you do this here by multiplying by cos n psi, and you do this here by multiplying by sine n psi. So once you do this, and you have to do this for n equals 1, 2, all the way to n. Remember again, this is a finite Fourier series. And once you do that, you are going to get a set of equations which you can then solve, and that will yield the solution to you in terms of the values of beta 0, beta nc, and beta ns. Now, whenever you do these Fourier series type of methods, you are going to need all the trigonometry you studied in high school and may have forgotten. So some of the simple identities are shown here. You may remember sine 2 psi is 2 sine psi cos psi, and some of these ones, because all these products and so on, such as sine square psi, cos square psi, sine psi, cosine psi, need to be expressed in terms of the integer harmonics. What I mean, sine 2 psi, cos 2 psi, and so on. Similarly, the cubes need to be expressed in this form. So in terms of again psi and 3 psi here, and you may get expressions such as these, which you need to again express in this form. So you may get expressions beyond this, and you will need to figure out the trigonometry which is out there to solve some of these problems. Now, much of this manipulation is actually quite simply done using some of the symbolic toolboxes which are there, such as Mathematica and also to some extent MATLAB and also Maple. So you may use some of those to actually express some of these products in terms of the harmonic content. So sometimes people express what is the need to study trigonometry in high school. Well, one of the reasons is, as you can see here, the identities come up in harmonic balance method and solution of periodic equations. Now, beside these Fourier series type of methods, which are essentially giving you the steady state solution, there are also methods which solve this solution using simple numerical integration in time. So in these cases, the differential equations are integrated in small steps of time. And this is the well-known approach to solve a differential equation numerically. You will find it in any numerical analysis book. That is very general, that is not specific to rotor system. So you can use that. The advantage of such an approach is that with the initial conditions, it is also going to give you the transient response of the system, whereas the current methods are only concentrating on steady response. But most of the time your vehicle is actually flying in the steady state conditions, so the steady response is often very important. But sometimes you do need to also find out the transient response and know how large the magnitudes are in terms of the transient response. Now, as far as time integration is concerned, there are many solution procedures. The Rangakuta method is very well known. You can find a lot about this by searching in Google itself. Then there is the gear method, which is sometimes used because in rotor dynamics, sometimes you land up with stiff differential equation, and the gear method may be good for that. So again, depending on what method you have, you can try them out, you can experiment them, especially if you're looking at both the transient and the steady state solution to the problem. So again, remember, whenever you solve a problem for transient and steady state, the answer depends in terms of the initial condition used, and therefore after some time the transient tends to die out and you are left with the steady state motion. So we'll end this response part today, and next lecture onwards we are going to start concentrating on the source of the right hand side terms, that is, how does the m beta come about. And so we are going to have to dig deeper into the fluid mechanics aspects of the problem. So I will see you then.